Section 6.4 talks about conditional probability and independence, and we're going to talk about what independent events are in just a little bit. So here's an outline of what we're going to cover in this section. So what is conditional probability? So conditional probability is the probability that event occurs given that something else has already occurred. Okay, so let's let E and F be events in our sample space. The conditional probability of E bar F, this is read E given F, is the probability of E occurring given that F has already occurred, right? It's also important that the probability of F doesn't equal 0. It has to be something that could occur. So let's say, for example, I'm flipping 2 coins in my experiment, right? And I want to know the probability of getting heads given that I've already gotten tails. This is when we could use this type of equation for conditional probability. So let's go through an example. So 20% of the employees at Acme Steel Company are college graduates. Of all its employees, 25% earn more than $50,000 per year, and 15% are college graduates earning more than $50,000 a year. So what's the probability that an employee selected at random earns more than $50,000 per year given that they are a college graduate? So let's let H be you earn more than $50,000 per year and C be a college graduate. So the probability of H is 25% because it's 25% of their employees earn more than $50,000 per year. The probability of C, we are told, is 20%. 20% of 20% of the employees are college grads. So let's convert that to a decimal, 0.20. And 15% are college graduates earning $50,000 more a year. If you're a college graduate and you're earning $50,000 more a year, those people are in the intersection of earning more than $50,000 per year and being a college graduate. So now I can calculate the probability of H given C. One thing I want to note is that H intersect C is the same as C intersect H. It's important to mention early on and often. The reason this is important is because, think about it, those same people would be in the intersection. We've just changed our notation. So that's the probability of H intersect C over the probability of C. So I've got the probability of our intersection, which is 0.15, over the probability of C, which is 0.20. That simplifies down to 3/4 or 0.75 or 75%, right? So what was my question? What is the probability that an employee selected earns more than $50,000 per year given they're a college grad? And the probability is 0.75, 3/4, or 75%, right? They're all equivalent. I've made sure that the answer is worked out for you guys in the PowerPoint, so you can use it as a reference. Next, let's let S be a sample space, and E and F are events in that sample space. Let's suppose the probability of E is 0.5, the probability of F is 0.4, and the probability of E intersect F is 0.01. So I want to calculate the probability of E given F. So for that, we take the probability of E intersect F over the probability of F. That's going to be 0.1. Sorry, this is 0.1. That's going to be 0.1 over 0.5. So I get 1/5 or 0.2, so 20%. Now I want to know the probability of E given F complement. So the first thing I need to do is I need to figure out, I need to find the probability of F complement, right? Because this is going to be the probability of F complement over the probability of E intersect F complement. So I need to find the probability of E intersect F complement. How am I going to do that? Well, one thing I really like to do is I like to draw Venn diagrams. I know. So here we have our nice little orange Venn diagram. I've got my sample space S. I have two overlapping events, E and F. Their overlap is 0.1. E has a probability of 0.5, so I'll put 0.4 over here because 0.4 and 0.1 add up to 0.5. I'll put 0.3 over here, so all of F has a probability of 0.4. E union F has a probability of 0.8, so that means that everything left in our sample is going to be 0.2. So the probability of F complement is going to be everything not in F. That's going to be 0.4 and 0.2. So I have the probability of F prime is 0.6. We could also have used the formula where probability of F prime equals 1 minus the probability of F, but I drew a nice picture, so we'll use that. Next, I want to look at the probability of E intersect F prime. So where does E intersect everything that's not in F? Well, it intersects at this 0.4 right here. So I'm going to have the probability of E given F complement is 0.4 divided by 0.6, which is 2/3 or 0.6666666 repeating, right? Or about 66.7%. Okay, let's change colors. Blue. So I want to know the probability of F given E. Remember what I said in the last slide, that E intersect F is the same set as F intersect E. So this is going to be the probability of E intersect F given E. So we put that over the probability of E. So I have 0.1 over 0.4, which gives me 0.25, 1/4, or 0.25, or 25%. What's the probability of E complement given F complement? So the first thing I need to figure out is I know already the probability of F complement. Go us. We figured that out. It's 0.6. But what I need to figure out is the probability of E complement intersect F complement. So where does E complement intersect F complement? So remember, E complement is everything not in E, and F complement is everything not in F. So it's going to be everything that's left over, which has a probability of 0.2. So that's going to give me 2/6, which is 1/3, which is 0.3 repeating, or 33.3%. So these are the probabilities, the conditional probabilities given this defined sample space.